Throughout this playlist, we explored one of the most important foundations of modern engineering. From simple signals and system models to Fourier analysis, sampling, and noise, every concept helped us understand how information moves through real-world communication systems. Now it's time to connect everything together and see the complete picture of signals and systems. At its core, communication engineering is about moving information from one place to another. Whether the information is a voice call, a video stream, a radar echo, or sensor data, it must be represented as a signal, transmitted through a system, and recovered accurately at the destination. The challenge is that signals rarely travel through ideal environments. Along the way, they encounter amplifiers, filters, communication channels, antennas, noise sources, and many other system elements that modify their behavior. Engineers, therefore, need a framework for understanding how signals change as they move through complex systems. This is exactly why signals and systems exists. Rather than studying every individual component separately, this field provides a universal language for describing inputs, outputs, transformations, and system behavior. It serves as the foundation upon which modern RF engineering, communication systems, and signal processing are built. We began by defining signals as carriers of information and systems as entities that transform signals. We then explored different signal types and learned how engineers model systems through input-output relationships rather than focusing solely on physical hardware. Next, we introduced linearity and time invariance. These two properties led to the powerful concept of linear time invariant, or LTI, systems. We learned that an LTI system can be completely characterized by its impulse response, allowing engineers to predict system behavior mathematically. Building upon these ideas, we introduced convolution. Convolution provided the mechanism that connects an input signal with a system's impulse response to produce an output signal. This concept unified our understanding of how systems process information and became one of the central mathematical tools in signal analysis. One of the most important discoveries in engineering is that signals can be viewed from multiple perspectives. In the time domain, we observe how signals evolve over time. In the frequency domain, we examine the frequencies that compose those signals. We learned through Fourier series that periodic signals can be represented as sums of sinusoidal components. Even complex waveforms, such as square waves, can be decomposed into harmonics. This revealed that many seemingly complicated signals have an elegant underlying frequency structure. The Fourier transform extended this idea to non-periodic signals, allowing engineers to analyze virtually any waveform in the frequency domain. From bandwidth analysis to filter design and spectral measurements, frequency domain thinking became a powerful tool for understanding communication systems and RF signals. Modern communication systems rely heavily on digital processing. To make this possible, continuous analog signals must be converted into discrete samples. The sampling theorem showed us that perfect reconstruction is theoretically possible when the sampling rate satisfies the Nyquist criterion. We then explored aliasing and discovered what happens when signals are sampled too slowly. High-frequency information can fold into lower frequencies, creating false spectral components and permanently corrupting the sampled signal. This demonstrated why proper sampling design is so important. Finally, we studied signal reconstruction and learned how digital samples can be transformed back into continuous time waveforms. Together, sampling and reconstruction form the bridge between the analog physical world and the digital processing systems that dominate modern engineering. Everything in RF engineering ultimately depends on signals and systems. Every transmitted waveform is a signal. Every amplifier, filter, antenna, and communication channel behaves as a system. Every wireless link is affected by bandwidth limitations, noise, filtering effects, and frequency domain behavior. The concepts introduced in this playlist appear repeatedly in advanced topics such as modulation, digital communications, wireless networks, radar systems, satellite communications, microwave engineering, software-defined radio, and modern signal processing algorithms. Engineers use these principles every day to design, analyze, and optimize real-world systems. Most importantly, Signals and Systems provides the intellectual framework that connects mathematics, physics, electronics, and communication theory into a single coherent discipline. Once these concepts are understood, many advanced RF topics become significantly easier to learn and apply. In this playlist, we learned how signals represent information and how systems transform those signals as they pass through communication and RF systems. We explored key concepts including impulse response, convolution, Fourier analysis, bandwidth, filtering, sampling, reconstruction, and noise. Together, these topics form the mathematical and conceptual foundation of modern signal processing and communication engineering. With these fundamentals in place, we are now ready to move beyond signals and systems and begin studying the physical world in which RF signals actually propagate. In the next playlist, Electromagnetic Fundamentals, we will explore electric fields, magnetic fields, electromagnetic waves, and the physical principles that make wireless communication possible. If you found this useful, like the video, subscribe, and follow for the next lesson.